Hello everyone, my name is Jiaqi Jiang, and I'm from Professor Jonathan Fan's group at Stanford. Today, I'm going to share with you our work on global optimization neural networks for the inverse design of photonic devices. Generally speaking, inverse design is to use optimization algorithms to discover optic structures for desired functional characteristics. It has been widely used for on-chip optics like demultiplexer, power distillator, and free space optics like metaservices, etc. Compared with conventional intuitive design using simple geometries, freeform inverse design is a way to push the design limits by exploring a much larger design space with more degrees of freedom. Since adjoint variable method make it quite efficient to calculate gradients of a Figma function simply by doing two simulations, gradient descent is a commonly used algorithm to discover optimal device pattern. However, most of these inverse design problems are non-convex in a very high dimensional space. Gradient descent as a local optimizer is easily to get stuck in the local design space, so that the performance of the final device strongly depends on the choice of your starting point. Here's an example that we are using gradient descent to maximize the device efficiency. As you can see in the efficiency histogram of optimized devices, there are several local optima. Actually, there are some global optimization algorithms like genetic algorithms, particle swarm algorithm, but they do not use the gradient information and are less efficient. Then there's a question for us. Can we come up with a gradient-based algorithm to perform a better global search? In this talk, I will first introduce the framework of global optimization neural networks, GLUNets for short, to solve this problem. Then I'm going to talk about its application to metagradient design and optical thin film stacks. Before we talk about GLUNets, let's describe the inverse design as an optimization problem. Here, x is the design variable of the device, which could be the geometric parameters or the refract index of the material. F of x is the objective function to be maximized or minimized. It could be the efficiency of a device or the difference between the physical response and the target response. This function can usually be calculated using a solver like the electromagnetic simulator. A representative relationship between the objective function f and design variable x in the complete design space is shown here, which is usually the non-convex. As you can see, there are several log optima, and x star is the globe optima. So the optimization objective is to find x star. Usually, we start with a random x in the design space, and using the solver to evaluate the function value and calculate gradient. Then we update the design variable x iteratively using gradient descent or ascent until it converges. So it may end up with some log optima as we've seen previously. This method is usually named as the topology optimization in the photonic design. The idea of the GlueNet is to introduce a generative neural network to produce the design variable x of the device. The inputs of the generator is a random noise vector z, which is usually sampled from the uniform distribution or standard Gaussian distribution. The generator is basically a complex function with trainable neural net parameters phi, and this function maps different z onto different device pattern x. So it can be regarded as a random device generator corresponding to a probability distribution p phi, which covers the whole design space. As we change the neural net parameter phi, the distribution p phi will change accordingly. Now, we're reframing the problem as optimizing the distribution of devices from the generator instead of a single device. The optimization objective function also becomes the expected value of f under the distribution p phi, which should be the integral of f of x multiplied by the probability p phi over the whole design space. When this objective function is maximized, the generator should be able to produce device pattern as a global optima with 100% certainty. In practice, it's not realistic to evaluate the expectation with infinite number of samples. So we just generate the batch of devices from the network in each iteration as an approximation. And the loss function of the network is defined in this way. There's a minus sign here because the loss function is to minimize as the convention of network training. The use of exponential is to emphasize more on the contribution from high-performing device X. So the network training will be biased to those devices in the promising design space and ignore devices with bad performance. In the training process, the batch of devices from the generator are evaluated by the solver, and their gradients with respect to devices are also calculated. Then the gradients backpropagate to the network to calculate the gradient with respect to network parameter phi by the chain rule, as shown here. And the network parameter phi will be updated using gradient descent. Therefore, the network is iteratively trained until it converges. Initially, the generated devices has a uniform distribution to cover the whole design space. The devices in the batch are very different. In each iteration update, since all different devices share the same generator, the generator knows the figure merit value and gradients of the whole device ensemble. The distribution of generated devices evolved as a group. In other words, the gradient from individual devices will impact the entire mapping from the noise to all device instances. This crosstalk between all devices are quite useful because devices in the permissive part of the design space will bias the overall distribution of devices towards those permissive regions. Therefore, log optima can be mostly avoided. Finally, the distribution of the generated devices will gradually converge to a cluster around the globe optima. Now we're going to look at application of GloNet for the inverse design of metagrading. Metagradings can be used as building blocks for large-scale met services. Here, we consider a 1D metagrading deflector that deflects normally incident light to a specific angle. The metagrading consists of silicon nanoridges on top of silicon substrate. One grading period is divided into like 256 segments, and each segment has a refractive index value between air and silicon. The deflection efficiency is defined as the outgoing power in the desired direction normalized by the input power. We will find the metagrading structure to achieve the highest deflection efficiency. With GlueNet algorithm, a generator is used to produce the refractive index profile of metagradings. The physical response of metagrading can be simulated by RCW simulator, and the adjoint variable method shows that the gradient of deflection efficiency with respect to refractive index can be calculated using two simulations. The forward simulation that propagates the normally incident light from the substrate to grating, and the adjoint simulation that propagates the light in the desired outgoing direction from air to grating. GlueNet generates a batch of different metagradings in each iteration and updates the generator by backpropagating all their efficiency gradients through the network. Furthermore, we also add a regulation term to the loss function for binarization. When this term reaches its minima, the device pattern will become binary. Here are some optimization results. The thickness of grating layer is fixed at 325 nanometers, and the wavelength of light is 1 micron. As a benchmark, for each deflection angle, we first use topology optimization to optimize 500 devices, starting from random grayscale patterns. The efficiency histograms are shown in the top row. As we can see, topology optimization often gets stuck in local optima, which wastes a lot of computation time. Then we use the well-trained GloNet to generate 500 devices for each wavelength and angle pair, shown as a blue histogram. Clearly, GloNet does not easily get trapped, and the peaks of efficiency histogram are located at very high efficiency end. Here, we show the comparison of the best overall devices for different wavelengths and the angle pair. These are efficiency heat maps for wavelengths ranging from 800 nanometers to 1200 nanometers, and the deflection angles ranging from like 40 degrees to 70 degrees. Statistically, 90% of devices from the GlueNet have efficiency higher than those from the power generation, which verify that GlueNet is an efficient and better algorithm for inverse design. Here's a movie to visualize the optimization process of the GlueNet. Device patterns are projected onto a 2D plane using principal component analysis. The variance of the stars stands for the diversity of the generated patterns. The color just represents the deflection efficiency. As the optimization goes, the distribution of devices gradually converge to a high efficiency cluster. Let's play it again. It looks like initially the distribution searched the whole design space and finally converged to a permission region in design space. Now, we're going to look at another application of GlueNet, the optimization of optical thin film stacks. Thin film stacks have been widely used in many optical systems, including passive radiative coolers, efficient solar cells, broadband spectral filters, etc. The materials and the thickness of thin film layers have to be carefully optimized to achieve the desired transmission and the reflection properties. To be more specific about the design variables, the thickness of each layer is a continuous variable, while the refractive index of each layer is a categorical variable, which can only take discrete values from a material library. The target reflection spectrum is defined on a certain range of wavelengths, incident angle, and the polarization, which is denoted by R star. The optimization problem is then posed as finding the proper N and T that produce reflection spectra as close as possible to the target spectrum. This is also a non-convex optimization problem. Design methods based on physical intuitions result in limited performance, and they are generally difficult to scale to aperiodic thin film stacks compressing many layers. To address this limitation, various global optimization approaches have been explored, including particle swarm, needle optimization, and the genetic algorithm. These methods are all derivative-free global optimization methods. They search the design space through the evaluation of a batch of samples without any gradient calculations, which actually limits their ability to reliably solve for the global optima. Here, we're going to show that how to use GlueNet for these problems with categorical constraints. Same as before, we use the generator to produce a batch of thin film stack configurations, including the thickness vector T and the refractive index vector N. Then, those thin film stacks are simulated by transfer matrix method to obtain their reflection spectra. The transfer matrix method is a fully analytic and hash-based solver for thin film systems. Instead of using adjoint variable method to calculate the gradients of the spectra, we basically program the TMM solver within the automatic differentiate package in PyTorch. It allows gradient to be directly calculated using the chain rule. So the TMM solver is compatible with the computational graph of the neural network. Next step, the gradient of the loss function should backpropagate to the generator and update the generator. However, refractive index n can only take discrete values. The gradient of the spectra with respect to refractive index n is not valid. To overcome this difficulty, here we introduce the probability matrix method to make it continuous. As shown in the figure, the network first outputs an n by n matrix A. Here, n is the number of layers in the thin film stack, and m is the number of materials in the library. Each atom of matrix A can be varied continuously, and take any real number value. A softmax function is then applied to each row of A to generate the probability matrix, just because it produced a properly normalized probability distribution. The S row of the matrix P is a 1 by m vector and represents the probability distribution that the S thin film layer takes on particular materials within the library. The output of the network now becomes the expected refract index of the S layer, which can be calculated using the probability matrix P. The expected refract index actually can continuously vary and allows the gradient from the TMM solver for backpropagation. Here, alpha would be a hyperparameter that tunes the sharpness of the softmax function. Initially, alpha is set to be 1, and the expected refract index has contributions from many different materials in the library. Over the course of network training, alpha is linearly increased until the probability distribution of each layer is effectively a delta function, which means the expected refract index has converged to a single materials. Now, the optimization is done. Here, we apply our algorithm to optimize incandescent light bulb filters as an example. In this design problem, the thin film stack should transmit visible light and reflect infrared light. So the emitter heats to a relatively higher temperature using the recycled infrared light, which can be used to enhance the emission efficiency in the visible range. Here, we're going to show the optimization results of GlowNet and the genetic algorithm. The green dots here are target spectra, and red dashed line represents the reflectivity for the normal instance. The blue curve represents the reflectivity averaged over all solid angles within 0 to 80 degrees, and also averaged for both T and TM polarization. It's obvious that GlowNet is able to find a better thin film stack configuration, which produces spectrum closer to the target spectrum. Besides, since the GlowNet takes advantage of gradient information, it requires a smaller population size and therefore more computational efficient. To evaluate the enhancement of the visible light emission due to the filter, we need to compute the emissivity enhancement factor. In the left figure, we show the emissivity power of blackbody incandescent source drawn in the black dashed line, and an equivalent source sandwiched by the optimized filter in the blue line. And the purple shaded region represents the human eye sensitivity spectrum. So the emissivity enhancement factor is then defined as the ratio between the light power received by human eyes from the emitter with or without filter. The emissivity enhancement as a function of number of thin film layers is shown on the right figure. We can see that a 30-layer thin film stack optimized by GlowNet has the equivalent emissivity enhancement as a 45-layer thin film stack obtained by the genetic algorithm. This result just demonstrates that the ability of GlowNet at finding optimal devices. At last, I'd like to talk about the architecture of the generative neural network. The network architecture is also an important aspect in GlowNet algorithm. A proper architecture can speed up the convergence and find better optima. There are many different architectures developed in the computer science community. It can be as simple as a shallow network, which only consists of one linear layer, one batch normal layer, and a nonlinear activity function. We can also stack multiple shallow networks to construct a complex generative model. And one efficient deep network architecture would be the residue network, or ResNet for short. It adds skip connections for each individual network block. ResNet allows some network blocks to be ignored by taking the skip connections path. Therefore, ResNet can be regarded as a mixture of shallow networks and deep networks. This property actually makes it quite suitable for GlowNet because for a complex optimization problem, we wish to construct complicated distribution in the design space, especially in the early stage of the training. And at the end, we hope it converges to a simple distribution around the optima which can be represented by a shadow network. Empirically, we would like to choose the network architecture according to the complexity of the inverse design problem. For low-dimensional problems, the shadow network works more efficiently because the number of network parameters is much less and is easy to train. For high-dimensional problems, the deep residue network works better at finding the optima because its capacity of searching the whole design space, especially in the high-dimensional space. This is still ongoing research, and we're going to have more understanding of the network architecture in the future. As a summary, in this talk, I have gone over the framework of global nets and have shown that global nets are an effective gradient-based global optimization algorithm for inverse design. Such a global search in the high-dimensional space is possible just by optimizing a distribution of devices produced by the generating networks. We also show that global nets can apply to the map grading systems, optical thin film stack systems. Actually, global nets can generally apply to physical systems where gradients can be efficiently calculated. Thanks for listening.